Okay, so welcome back. This morning we're going to have the final lecture in James's series. James?
Thanks. Actually, let me thank you guys also. This is the first time I ever presented the proof. I sound very loud. Am I very loud?
No.
No, okay.
It's good.
Pleasantly loud.
It's the first time I ever presented the proof in full, and okay, so I promised to make some use of it, both in revisions to the final version of the paper on the archive, and also in some lecture notes that I'm writing right now. So, by the way, I mean, it's I'll do the sort of small recap of the overview of the proof again, but much of the proof is, as with many things, like better understood in context. And actually I'm teaching a course right now at Washington. So if you go to my webpage, there are lecture notes. So for instance, all of the stuff with sum of squares and the relation to PSD rank is much simpler in the setting of non-negative rank and the corresponding degree notion of the Junta degree. And like on my webpage, on the course webpage, you can find lecture notes doing the same thing we did in that setting. So it's sort of easier to understand things there if you really want to. And then the stuff with this entry maximization, I mean, there's actually a whole theory there of many fields, and the name of the course is Entropy Optimality. You'll find also some lecture notes about those things. So just if you're interested, there's additional material. Okay. Now I can finish and hopefully talk about some open directions. Let me now remind everybody what's happening. We had this g. This is sort of the hard function we start with. So let's let d, as before, be the sum of squares degree of g minus 1. And we said we have a proof that that g doesn't have a small sum of squares degree in the form of a functional that separates between the two cases. So if you take the inner product with g, you get something negative, and if you take the inner product with the square of a low degree polynomial, you get something non-negative. So this is universally, if g has large sum of squares degree, or it has sum of squares degree d plus 1, universally the way to show that is with such a functional. And then our goal was to sort of lift the fact that this thing has large sum of squares degree to a lower bound on the non-negative, or on the positive semi-definite rank of some matrix. That matrix defined like this. So well, it's just all the evaluations of g on restrictions, but now, okay, so these are restrictions, these subsets of size s. And now x is coming from 0 on to the n. And your goal, which we now finished today, is to show that the PSD rank of this matrix is large if the sum of squares degree is large. So it's at least some constant that depends on g. So you should think here, I'm not writing the quantifiers again, but n is going to infinity, g is fixed. I'll mention what happens if g depend on n at the end of the talk. But this is the basic setup. So, and again, let me remind you, this is joint work with Rosado Ravendra and David Storr. Okay, right, this is the goal. We define this matrix derived from G, and then we want to show that it has large positive semi-definite rank. And in particular, though we did on in the first two lectures, is to show that this gives a lower bound on the size of any semi-definite program characterizing the cut polytope. Okay. At the moment, it will be super polynomial. If for every exponent, fix some g with sum of squares degree that large, and you'll get a lower bound that grows like n to that degree. And you can get something exponential, or something like 2 to the n to some power. We'll discuss it at the end. But this is the goal, just to remind you. And okay, so let's let's remember, so let's write down what it means that this matrix has PSD rank R, and then we'll recall the proof outline. So it means that we can write M and G as trace of AS BX, where AS and BX over the whole range of indices here, this is the range of indices, are positive semidefinite matrices of so R by R positive semidefinite matrices. This is what the PSD rank means. And so our goal is to prove a lower bound on this, to show that if R is too small, this is an impossibility. Unless R is less than this is an impossibility. Okay. And the way we intended to do that was actually to lift this separator to a separator which separates G from any representation as a sum of low degree squares to a separator that would separate this matrix from any representation like this with any small positive semi-definite rank representation. So the first thing, okay, so here, what's the functional? It looked like this. So this is how the functional looks when you apply it to the left-hand side. So the functional is just averaging against this kernel, which is a function of x and s. And we said that this is precisely the inner product between phi and g, which is negative. Okay, so from the left-hand side we get a negative inner product. And now our goal was to evaluate the same thing on the right-hand side. So to that end, let's before we write down the second thing we know, let's just make a definition. Okay. So if we have a function that maps 0 1 to the n, this R is going to represent the square root of b, so I'm not going to require, the square root is still positive semi-definite, but I'm not going to require R to be PSD, because it's not needed. We'll just require that R is a symmetric matrix. And then let's define, I just want to define a shorthand for this thing applied with R, with the square of R. Okay. I'm going to write R of x here just so that you remember R as a function. It's written above, but it probably helps. Okay, so S, X, average like this, alright, square. Okay. So I just defined this thing where I replace b of x by r of x squared. Just because I don't want to have to write square roots all the time. That's the reason. So now, how could we translate our goal here?
So the expectation is?
Expectation, as always, is over a uniformly random s of size m and x from 0 1 to the n. So anytime you see s and x, that's what the expectation is over. Yeah, if you think there's a type error here, what's the so the only issue here would be this thing, right? This is an n-dimensional vector, but S is size m, so this restriction is an m-dimensional vector.
The Rx squared in the end is not
Rx square is so this is, and by the way, this is the matrix square of Rx. So I take the matrix and square it.
And towards?
No.
No. Okay.
How should we? I mean.
Okay. Sorry.
I don't know if that helps, but it somehow helps. The matrix square of Rx.
So then that phi is over m.
This phi is on. Yeah. Well, maybe this was the problem. Phi is supposed to be on m things. Already here we had a problem. It wasn't. But phi is on m things. Yeah. So this is on. Thank you. Okay. So now we can translate our goal. Restated as just proving that phi, and again, I'm going to write, okay, so what this means is you take b of x, it's a positive semi-definite matrix, so you can take its square root as a matrix. That's what, so I'm applying it to that matrix value function. Well, our goal is to show that this is bigger than what we would get for the left-hand side. If R is too small, right? So somehow if the rank of the factorization is not big enough, we would like to show that when we apply this thing to square root of b, we get something bigger than we got here. And if we prove that this representation cannot exist, because phi applied to square root of b is exactly this functional applied to the right-hand side. I mean, this expression here, you just replace this by b. That's what happens if you plug in the square root. You just get this functional applied to the right-hand side. And so if it's bigger than it is to the left-hand side, we derive a contradiction, so it cannot be. So this is our goal. Now, towards that goal, first we did one easy thing. It was mostly for inspiration, which is that if the degree of R, okay, and you should also remember, okay, this is the first time I write the degree of a matrix. This is just the maximum degree of any entry of the matrix R. Okay, so every entry is R by R matrix, little r by little r matrix. Every entry you can think of as a polynomial, a multilinear polynomial. This is the maximum degree of any entry. So if the degree is at most d, this is what we saw before, then when we apply this to R, we get something non-negative. It's just because at the end of the day, when you apply this to an R which has degree at most d, then this thing is hitting here only low degree squares in the expansion, and when this thing hits a low degree square, it always outputs something non-negative. So, okay. And then what we did yesterday, so okay, of course our problem is that square root of b is not necessarily low degree, but what we did yesterday is we said there exists an approximator such that two things hold. First of all, the degree of the square root of the approximator is not too big. So the degree we got was order log r over epsilon. Epsilon is coming in just a second. Times this times this. Okay. Which, by the way, you shouldn't. So you should think about phi and m as both constants that depend on g. So really, this is just order log r. And the property we had was that the sense in which b tilde approximates b is that phi of b is at least, phi of square root of b. The square will help us in a second. It's hurting us now, in terms of notation. Okay. So if we apply this to phi of square root of b, it's at least what happens when we apply it to the approximator minus epsilon. This was in fact this was the notion of approximation, to say that to say that on this sort of this linear test, sort of b tilde is not doing too much worse than b. Okay? So you see sort of where we're going. We're almost done because we want this thing to be. So this quantity here is negative. We would like this thing. We're not going to get this thing to be positive, but we'll get it to be very close to 0. So we just need it to be closer to 0 than this negative number. So you can see where we're going. We can lower bound it by this thing, which has somewhat low degree. And so then if we had maybe a stronger n log of 1, we would be done. Because for this thing, we would say it's greater than equal to 0. Of course, we won't get it greater than equal to 0. We'll get this thing also being at least minus epsilon. So then this whole thing is minus 2 epsilon. So now if we set epsilon to be this over 1/3, we would have separated the two sides. Okay. So then now let's write down the lemma, which is the final statement. And by the way, I should remind people that if you remember, yesterday we scaled things so that the average value of this matrix is 1, which gave us the fact that that the expected trace of B is 1. And so we maintain that property in the approximator. This corresponds to working with density matrices last time. Sorry, is equal to 1. That's just a normalization issue, which is necessary, of course, because otherwise we could do much better on the test just by scaling. Right? I guess. I think we could cheat by just doing something if we didn't insist that they scale the same way. Okay, so now the final goal, it completes everything, is to prove that phi, okay, again I missed that. So it's basically to prove a stronger version of this, well, something which assumes a weaker degree bound on R and manages to get something which is not 0 here, but something minus something very small. So if the degree of R is at most, say, L, then the way I set it up, it's gonna look a bit ugly, but then we'll see. We'll simplify. So then the claim is that if we I want to prove a generic lemma in a second, but I want you to see how it's going to apply first. So let me just apply the claim to B tilde. So the claim applied to B tilde is going to be that this is at least minus square root 2 times the maximum value of the separator phi. You should, by the way, I mean, this is appearing all over the place, so you should think of this as a measure of sort of the complexity of the proof that G has high sums of squares degree. But unfortunately, it's appearing all the time, and it is the worst factor of all the bad factors. Okay, so we get this times R times the rank, and then times the following expression, L m over n minus m to the d plus 1 over 2. Okay? And honestly, this is going to be a universal constant because this r is going to become a universal constant, so it won't be square root of 2. We look at this, and now you say, what is this parameter L? Good question. That's the degree of square root b tilde. So, so you actually, this is the degree of square root b tilde. So now let's suppose we had this claim. Let's see how we finish. Well, we know the degree. It's okay. So let's okay. So the first thing we know is that this is order log r. Now we have to be careful in this order because the order is depending on is a constant depending on g. Let's just verify that the constant really only depends on g. N depends on g comes with the domain, so n is depending only on g. That's fixed. This is fixed. When we need to choose epsilon to be here, well, we already saw it's this divided by 3. Again, something that depends only on g. So this bound is order log r, where now you have to remember that there's a constant here depending on g. I'll tell you the dependence at the end, but I want to do the argument dependence. So then, if we use this, then this is minus some constant depending on g. Okay, so there's lots of things that are constant depending on g. Now this m is a constant depending on g. This is a constant depending on g. So we just get r times n to the there's a log r, which is, if we don't know, not just depending on g. Log r over n to the d plus 1 over 2. That's what we get here. So I just got rid of the m's and replaced them by a constant depending on g. It was a constant inside the exponent, but the exponent only depends on g, so I can move it to a constant outside the exponent. And now you will see that this is where the rank lower bound comes from. If you look here. Because, in order to, basically, in order not to have a contradiction, in order that we don't separate the two sides, this thing, let's say this thing has to be at least, this thing has to be, it's a negative number, so what does it mean? Okay. Forget the negative part. This thing has to be at most, say, 1/3 the distance of this from this thing to 0. Okay. If this thing was small, then we would get, minus epsilon minus this small thing, and if they were both, so if we choose them both to be small, then we'll contradict this separation. Okay. And you see what's the scaling. Again, this is a constant that depends only on g. So this implies that r needs to be at least some other constant times n over log n to the d plus 1 over 2. And just, by the way, if the log r wasn't there, you'd see it immediately, because then it's just, if you ignore the log r, then it's just r times n to the minus this. So to avoid that going to 0, it must be that r grows fast enough. To avoid that this product is not epsilon over 3, it must be that r is at least this thing times epsilon times a constant. So the only issue is the log r, but the point is that you can just, the simplest thing to do is just say, well, if r is at least n to the d, then we're done, we already have our lower bound, and if it's not, then this log r, so either r is at least n to the d, and then we have a check mark, or otherwise log r is at most d log n. D is a constant that depends on g, and that's where the log n is coming from. Okay. So you see, if we can establish this claim, then then we're done. And this is the point. This is the place where the lower bound is coming from. Basically, you see, there's a degree reduction going on here in some sense. Like the degree is, so somehow this, if the degree L is small, then we get this drastic decrease in the error, the distance from 0. So the point is that we can establish this, then we're done. And it's just it's like a soft version of this thing, but where we can tolerate much higher degrees. So by the way, if you're thinking about, if you want to just think about this qualitatively, here you could even have L be n to the 0.99, and life would still be good. You'll still get n to the minus d times some constant. You won't get d over 2 here, you'll get some other power of d. But the point is that, the requirement on the degree here is fairly weak. It just needs to be, in order to get some non-trivial behavior, like that r has to grow like n to the constant times d, you could even just take your L to be n to the 0.99. So, yeah. Okay. Obviously then you should take m to be, you don't want to get n here, so you should take n to be something, n to the 0.001 or something. But just the point is that the degree of your approximator, it has to be slightly non-trivial for this argument to give you something much stronger. So it has to be much less than n, but this is not, okay. This is very small degree, but it's, you can imagine smaller degrees. Okay. So now the reason I did this is because I'm gonna now write the claim in a slightly more general way that'll make the proof easier. So now here's the formal lemma. Okay. For any Q that's mapping sets to symmetric matrices, and we'll just use R as this, you can think of R in the same way. It's mapping 0 and 2 symmetric matrices. The following holds. And when we look at square, it's at least, I apologize, it's actually, nothing is going to be too bad, it's just that there's like, a lot of error terms. Okay, so first of all, we're going to get what we want here, which is degree of r times m over n minus m to the d plus 1 over 2. That's what we want. Okay, and then, actually we don't need the square roots. Maximum over s of the maximum eigenvalue of qs, and then we'll have here qs r x squared, and then we'll have here, what is it? Don't worry. But it's, okay. But, okay. So now if you want to apply this here, no, if you want to apply it up here, then you set q of s to be the square root of as, and then r of x is the square root of b tilde x. And then, remember that this thing is equal to trace of q. Yeah, if this formula doesn't just strike you as completely obvious, then just go. It's true. And you write it as a product. So the point is that since this is equal to this, if we plug in these values, we get exactly trace a of s times b tilde x, which is the quantity we want. So we are in fact measuring this on the left-hand side. And then the point is that here we know that we know what the operator, we have a bound on the operator number of as. We didn't write that again, but it comes from the truncation and rescaling. So we know that that's at most r squared. Okay, that's what we proved last time. It's a constant times r squared, but let's not make things even more complicated. Okay, so here you get r, because this is the square root of a. So the maximum eigenvalue is the square root of the maximum eigenvalue here. So the point is, so you plug a here, you get square root of r squared, you get r. That's where the r is coming from. Okay, so we see this term. We see this term. This thing is okay. Yeah. So now you use the fact that the other thing that came from the scaling, which is that the expectation of as is the identity, and then if you look at what you get here, you get. So this term becomes, when you plug in q to be square root of a and r to be, say, b, then this term is expectation over x and s, trace as b tilde x. But we have this equal to identity, so this is just the expected trace of b tilde x. And if you look, hopefully over there we wrote that this is equal to 1. So this just becomes 1. And also, now we're going to do, this thing is equal, this thing is just, remember, r is the square root of b. So this is exactly just equal to, again, to the expected trace of b. So when we plug in what we care about, this becomes 1, and this becomes 1, and this becomes r, and this becomes exactly what we wrote. And the only reason there's a constant here is because that's not really r squared. That's constant times r squared. Okay, so the main point though is now you can forget about in the lemma, which we'll now prove, depending, it's we'll now prove it. Let's just say confidently. You don't have to remember any properties of a or b or anything. The lemma is just, here are all the assumptions you need. Q is symmetric, R is symmetric. That's it. So the point is you get rid of all the, here in all the red, we wrote down all our assumptions. We get rid of them, now we just have the statement. And let me just say qualitatively what's happening. And then maybe we take a vote on whether to do it. I feel like I know the outcome of the vote already. Or maybe, I have a feeling I know people voted in secret what they would vote. the basic idea is, I mean, we want to, the basic idea is something like this. We have phi s x, and then here we have qs, we have rx, and the Frobenius norm squared. And we have this averaging on s on the outside, and degree of r is like n to the 0.99. So it's small, but it's not small enough where we can use 0.2 to say something interesting about it. In other words, so remember, when we hit any low degree square by this thing, we get something non-negative. This thing turns low degree squares into non-negative things. Okay, so notice that this thing doesn't depend on what's going on outside of S. So here's the whole thing. Here's S. Sorry, I may just rewrite this. It's the same. This was our definition from yesterday, but we didn't define it again. So this thing only depends on the bits of X inside S. So this averaging over X, we could move the portion. We could move the portion on the complement of S. We can move it inside because this thing doesn't depend on that. So the point is, we can move the average over all this stuff in here. Okay. And now let's just see Fourier analytically what that corresponds to. So just in the real case first. So suppose we have an F. In a second, we're going to have to do a linear transformation so that 0 on n becomes minus 1, 1 to the n. Notice that nothing bad happens. The only bad thing that could happen is that the degree doesn't change under this linear transformation, so we're fine. That's just so we can do Fourier analysis in a natural setting. But okay, so we have some real valued function f. And suppose you think about, and in fact, let's break this domain into two pieces. So one piece is S, and then the other piece is just whatever is left. S bar. Yeah. So suppose we average. We think of the function that maps y to f x y, where x here is averaged over minus 1, 1 to the s. And in fact, let's not think about the function that maps y there. Let's think about the function that maps ys bar. I know I'm standing in the way of what I'm writing, so hold on. Yeah. Okay. So this is just a function on minus 1 to the n. I just split the input to the function into the bits in s and the bits in the complement of s. And now, of course, the function on the right-hand side doesn't depend on what's in s because I'm averaging over everything in s. And the question is just so let's define I ran out of space on the board, but let's define this as f. So fs. Okay. So it's just f, but now we add, when we get some input, we average over everything outside of s. So the point is that what this does is very nice in the Fourier basis. It just kills every Fourier coefficient that's not contained inside S. So in the Fourier basis, this is just, okay, so the chi alphas are the basis elements. I'll just remind you what F looks like in the Fourier basis so that you can compare the two. Okay, so F looks like this in the Fourier basis. The claim is that when we average over everything outside of S, just everything where the character, the set is not contained inside S, becomes 0. And that's just because if you have any character, some set T, when you flip this input from 1 to minus 1, the sign of the character changes. So if you average it with both signs, it cancels out. So this is what happens in the restriction. So you see that the restriction has this nice, just if we look at real value function, there's a very nice sort of degree reduction property, which is that when you go from here to here, think about choosing now a random set S and applying this restriction. Large monomials tend not to survive because in order for a monomial to survive, like in order for a monomial xt to survive, it has to be that t is contained completely inside S. And if you have a large monomial, this is very unlikely for a random set S. So you can imagine that this process of averaging over the complement of S is reducing the degree. We have one, we solved the problem in just a second, but one seemingly serious problem here, which is that our setting is not that we have some f and we do this. Our setting is more like we have a function g, and we do this process to the square of g. Right? And what we would like to have at the end is not something low degree. What we would like to have at the end is something, which is the square of a low degree polynomial. Okay? So I hope we see the difference. Here you average on the outside. Okay? So definitely the degree of the right-hand side, when you choose a random S, the degree of the right-hand side should shrink drastically, because exactly for the reason it shrinks for F. The problem is that if I have degree something, say at most k, and I know that it's, let's say I even know that it's non-negative everywhere. What can you conclude about, let's say, okay, the degree of h squared is k, so it doesn't matter in all the case, not negative. The degree of h squared is k, how can we write h as the square of a low degree polynomial? And the answer is, in general, we can't. In fact, if we could, the whole problem would, we would have stopped the lecture on day one, because g itself, so any positive function, in particular g itself, so take g. So it's positive, so I can take the square root. The square root is a polynomial on 0, 1 to the n. So g is the square root of g squared. So in fact, after we square, we get a low degree polynomial if g was low degree. Remember, our g was quadratic. The g we're using, we've long forgotten it, and it was the knapsack polynomial, so it's a quadratic function. So the degree of the square is low degree. The degree of the square is 2. But of course, the degree of square root g, hopefully, we know it's at least n over 2. So in general, the point is that averaging outside the square, while it will give us something low degree because of this degree reduction, it's a little tricky that it doesn't necessarily give us the square of something low degree. Sort of in other words, let me say one more way. If we did this, we're happy. This would be awesome. If we allow ourselves to do this operation, to average inside the square. Let's put it. I know I just defined g as a knapsack, but for any f, if I allow myself to average inside the square, I'm really happy. This thing had medium degree. Now under the restriction, it has low degree, and I get a low degree square. But that's not the operation we're allowed here. What happens is we average outside the square. So this thing will again be low degree because the random restriction lowers the degree, but there's no reason it should be the square of something low degree. This is on a game show. But this is fantastic. Okay. So the main point of this lemma, which now I talked long enough that we don't need to prove it, is that basically what you get as a result of this random restriction is that the restriction of f squared is basically this plus some error. Okay. So so this is what we can do. This is what happens. We average over everything outside S. We take a medium degree square, average outside S. It turns out that this is the square of the low degree part plus some error, and the error is what comes into the denominator. Okay, so and then just to justify, so now that we're not going to do the proof, because I at least want to mention some open directions, just to justify where this bound is coming from, Well, first of all, there's some Cauchy-Schwarziness going on here. That's why there are all these square roots. Even this one is a square root. It's the square root of the normal q squared. And that's where this square root is coming from. But where is this dependence coming from? Like this L over times m divided by n minus m to the d. Well, if you just look here, you can say, what's the probability that a degree d term survives? So, so suppose we take a monomial. Take some monomial xt. We should think about this monomial as being one of the monomials in R. Of course, R is a matrix, so you have to actually, this will come with a matrix coefficient, but that's not important. Okay. But by the way, by this I just mean the product over I and t of xi. And then just what's the probability it survives? Okay. Well, we have to choose. I mean, in order for what is the probability that it survives? Good question. It's really what we want to compute. See the degree is about. Yeah. Okay. I see. It's not just the probability it survives. I mean, what's happening? I mean, the probability it survives is fine, but why am I, what's going on? This. Choose D. It's not what it's just, what I want to do is compute, here's what I want to compute. Now I just don't see why it's the most relevant thing, although it should be. I always want to compute the probability that t intersected with the set S is bigger than d plus 1, which is the bad event for us, that we get something with degree bigger than d plus 1 afterwards. Yeah, so this has to do with computing the square, which we didn't write out. Okay, so what we said is that if, in this linear relationship, if the set T doesn't fall completely inside S, then we get a contribution of 0. Okay. Unfortunately, when you square, what the calculation is that what remains is some weight on the Fourier coefficient of S intersect T. So the point is that if you start with something of degree that's the size of T, afterwards you could have a term remaining which is of the degree the size of T intersect S. This is a function of the square, which we're not going to get to see. So that's what this calculation is. It's sort of the probability this thing survives, except we're squaring, so it doesn't actually, it's not actually going to necessarily die off. Okay. I mean, I guess, hopefully, intuitively, it's not too hard to believe that this is a calculation that arises, that you sort of take T and you care about the size of intersection. Okay, so afterwards, if you want, I come up and we can just do it. But the point is just that this quantity, just to tell you where this is coming from. Okay, so what is it? It's size of T. We need to get at least D plus 1 things from T. So it's T, like at most T choose D plus 1. Then we need to select, we're choosing a random subset of size M. So totally we have N choose M subsets. To get a bad one, we have to choose D plus 1 things from T, and then we need to choose M minus D plus 1 things from the remaining N minus D plus 1 things. And there's a bit of overcounting there, because if the intersection was size D plus 3, there's multiple ways to count, but we've upper bounded it. And then you can just this is at most T m over n to the D plus 1, as long as long as d is more than 6. That's e is the base of the natural limit. Okay? And then you can just see where it's coming from. You know, d is a very small thing. So here you're getting to choose m things from n, and here you're making d plus 1 fewer choices from the large set, and d plus 1 choices from this tiny set t. So your gain is like 1 over n to d plus 1. And these things are sort of think of them as fixed, even tiny compared to n. Okay. So the point is, this is where the sorry, I should have put n minus m to be formally correct. Okay. So this is where that term comes from. Okay. So it's just when you do the calculation and use orthogonality of the of the sort of the high order, the high degree part and the low degree part of the matrix R. Okay, and you run through the calculation. Basically, you get this that this is equal to this plus some error which is small. Okay. And the form of this thing is just this calculation, like what's the probability that a large monomial that some monomial has an intersection with S. Okay. So it's at most this. So you can see where it comes up in the error. The error is basically the sum of the squares of all the high degree things, but every term you get to multiply, it only, in expectation, it only survives with this probability, so you get to multiply it by this. So sort of this is like, in some sense, okay, this stuff here represents an upper bound on the high degree mass of R, and not the high degree mass of R, actually, the high degree mass of this whole square. And this just represents the fact that every term there, the probability it survives is quite small. So in expectation, over S, you get some error which is small. Okay, that was so any questions? And I hope the idea here was clear. I was prepared to do the proof, but I guess I wasn't prepared to do it in less than half an hour by itself. Yeah, the proof is not so like the point is it's a homework exercise, not like maybe a start exercise, but you really just need to use orthogonality you write R in the Fourier basis, you use orthogonality of the high degree part and the low degree part, and then you just crunch through, you get the correct thing. Okay. So now I want to say two things to finish. Like what are some of the things we don't understand at all. So first of all, if you make the dependence on G explicit, and you're not just having to get a constant depending on G, then the lower bound you get looks like this. M and G, some constant which is now universal, times M squared over N, and then here's the factor that's really I guess it's really killing me. This is what you would get in general. Okay? Which makes sense. It's sort of similar to what we had before, except that now you want this separate, the lower bound for phi. You don't just want to know that there exists a separation. You want that it's somehow a robust separation. It's like a fat separation. So sort of it's how much separation you get scaled by how the infinity norm of phi, how crazy phi is. So this is the general lower bound that you get, except for the fact that this looks really, really good, and it's the inverse of what we want. So let's try one more time. I mean, it looks really bad. It's just it's the same thing, except I wrote it as something less than 1, and that would be a fairly weak rule of thumb. Well, I wrote part of it as a reciprocal and part not, so it was confusing to me as well. But this is okay. You get something which is good, like n over m squared. So from there you hope to even, and this d is supposed to be if you do this with Grigoriev, you do this, it's supposed to be something like this. Okay. So this looks really good. I mean, this gives you sub-exponential bounds, except for the fact that we don't necessarily have any control on this. And so what's the way that we got 2 to the constant, for Grigoriev, we got 2 to the constant to the 2 11s? Yeah. Okay. Well, we just, specifically for the knapsack polynomial, we just proved that that Grigoriev's implicit pseudo-density has small L infinity norm. So for knapsack, you can achieve this ratio to be, I believe, 1 over m to the 3/2. Constant over m to the 3/2. Just for the knapsack polynomial. And I guess as Troy will discuss today, this is fairly lucky. This is like a diamond in the, for other polynomials you try to apply it to, you'll get something which is much, much worse. Like exponential, like inverse exponential in m as opposed to m to the 3/2.
You can actually get m to the 1/2, right?
I'm dividing here by the separation, which I thought was 1 over m. So there's like the separation, which I thought is 1 over m, and then if you normalize so the expectation is 1, I think this is, I agree the infinity norm is root m, but I think that the size of the separation is only 1 over m. Once you normalize it to have expectation 1.
Oh, you're dividing g by...
This is the separation, and this is the... Okay. The important thing is, it could be better than this, but the important thing is that this is inverse polynomial m. That's what gives you a lower bound like this. And one can check. I think this is correct. Okay. So two things. First of all, this whole framework can be applied, for instance, to not just to like the cut polytope, but it can be applied to approximation problems, like max 3-set, given a 3-set formula, maximize, find an assignment that maximizes the number of satisfied clauses. And then you can do the same proof relates the approximation ratio achieved by any SDP to the one achieved by the Lacerre SDP for the problem. The problem, the issue there is that, okay, so for instance, you can show that any SDP in the model we've been discussing, say for max 3-set, has a 7/8 integrality gap, the sort of the trivial integrality gap, unless it has size which grows super polynomial. So n to the constant log n over log n. So, like using these methods, you'll plug in the lower bounds for max 3-set from Schenbeck or from Grigoriev, and you get this. But you'll notice this is much worse than something exponential, and the reason for that is that the lower bound for max 3-set is not like for the knapsack column. It's actually a fairly it's a fairly complicated object. And if you go to other problems, it gets even more complicated. And so the only bound we have we know a pseudodensity exists. The only bound we have is just a worst case bound, which is basically that when you're on is basically this. This is the only bound we have on the pseudodensity. Okay, on the ratio. So here let's say normalize the separation to 1. So the only 2 to the m much worse than 1 over poly m. Okay, so the point is, and so this is what stops you from having a tighter connection. Okay, there's no good philosophical reason why it gets stuck there. So the point is that for some squares, or for the Lacerre SDP, we know the size lower bounds to get better than 7/8 are exponential, 2 to the constant times n. So there's no reason that, and also by the way, this is necessary. I think this is necessary. Like only for this very special knapsack polynomial would this have a small norm. I think it's necessary that you have some large L infinity norm, but it shouldn't matter. So that's an unfortunate aspect of the proof. Like I don't feel like there should be a inverse polynomial dependence on phi infinity, but we don't have any conceivable way of getting rid of it at the moment. So that's one significant open problem. I will say that the only place it really hurts us, this phi infinity, it actually doesn't hurt us here. Here we're fine, and it's because we get to multiply by this like extremely small thing. So here actually phi infinity is not upsetting us. Where it's upsetting us is in the degree bound that we erased, but the degree here was, we actually paid attention to constants that depend on g. The degree here is scaled like phi infinity. So that's really bad. Because if, well, you can see, if this is 2 to the m, and you want to get any non-trivial degree bound, you're stuck choosing m at most log n. Right? N is a trivial degree bound, so, okay. So this is where you're getting killed. So it actually was in this max entropy approximation part of the argument that this is really painful. Okay, so that's one thing. There are lots of other reasons. I mean, it's a very cool problem to consider getting rid of this phi infinity. Maybe by like specializing the approximation problem, like maybe the version we stated is just too general. We don't assume anything about the tests. Okay, that's one thing. The other serious defect is that this doesn't work for anything except, so any domain except 0, 1 to the n. Okay, so we did it over 0, 1 to the n, but for instance, here's an open problem, which is just PSDs for perfect matching. Okay, so let me tell you the slack matrix, and then we'll end after I describe this. Okay, so let K to n be the complete graph on 2 n nodes. Just like this. This is the complete graph. And then define the following matrix. So for a subset of 1 up to 2n of odd size and a perfect matching x. Okay, so we have 2 inputs. We have a set and a perfect matching. Define m at Sx to just be, this is the number of edges of the matching crossing S minus 1. So it's like the boundary of S intersected with X minus 1. And pictures looks like this. Here is odd set S, and then X is some perfect matching, which may cross S in some number of places. So the point is, this is always non-negative because, well, if you have a perfect matching and you have an odd set, at least one edge has to go outside by just parity. And in fact, this is a slack matrix for the matching polytope. So these are all the inequalities for matching. So the question is the PSD rank of this matrix at most polynomial? And that question is wide open. My colleague Rothfuss proved that for polyhedral lists, so for the PSD rank, have a strong model for this matrix. So the non-negative rank. The non-negative rank is very big, but we have no idea about the PSD rank. And it would be really nice to just apply this framework to get a lower bound, because it would just reduce it to considering sums of squares, relaxations of matching, and those are now, for me as of yesterday, at least now I understand what's going on there. There were discussions over lunch. But the reason this doesn't work is because it's really married to having the sort of the functions on 0, 1 to the n. So the second you have some non-trivial constraints, like here, sort of like, you can think about encoding a matching as an element of 0, 1 to the n choose 2, just as an indicator set of edges. But of course, not every subset there is a matching. Then the proof breaks down, and I'll tell you where it breaks down. It's not in the degree reduction part. All reasonable things seem to suggest that you can use appropriate representation theory to get the degree reduction to go through. It's the fact that when you look at the sort of the random restriction, so this is the random restriction S, the picture, for the cut polytope, what we have here, like if this whole thing is, if you think about this whole thing as sort of being 0, 1 to the n, then what you have here is just a smaller, just a little cut polytope. It's adorable. You just have like a tiny cut polytope down here. Just this is 0, 1 to the s. So it just looks, it has this self-similarity property. But it doesn't happen for matchings. So for matchings, if you choose, and here this is sort of a measure theoretic statement. If you choose a random matching, so like even just fix a set S and look at a random matching, the matching intersected with S tends to have almost, if S is small, almost everything goes out of the set. Okay? So the picture down here looks very different from like the picture up here. And what it means is, in some sense, that if you assume that you have little lower bounds for every set S, like we did for the proof here, they're actually hidden in exponentially tiny pieces of the space. So whereas the lower bounds for G were sort of spread out everywhere, these things are like in the little nooks and crannies of this whole space. We just, if you think about like trying to do some kind of learning or figure out what's going on, it's going to take, you're going to get something much more complicated because the insights you have are very, very sparsely distributed around the space. So you have two options to fix that. You have two options to fail at fixing that. One of the options is you just say, okay, well, I'm still going to consider the uniform measure on sets and a uniform measure on matchings, and then I'm going to have my phi just only concentrate on matchings that look nice. So phi will only concentrate on, say, matchings that are like this blue matching, or like, okay, maybe with one edge going out. Then the L infinity norm of this thing is off the charts. It's crazy, and you don't get started on the thing. So that's one thing. The other thing you could do is you could say, well, I'll just choose the measure on S and X to be not a product measure. I'll choose them in a correlated way. I'll choose the set S and the matching together. And then, it's not clear, but then you could, then you can now get feedback to being very small, sort of like well-bounded. It was sort of, I guess you can't, I have no idea, I'm not sure anybody has any idea how to do anything with non-product measures in this setting. They really kill all kinds of things we use the whole time. So this is a fascinating open question. It has a number of connections to like communication complexity. Like if you know like about set disjointness, this problem is very similar to set disjointness. That's in fact the connection that Rothfuss used. And Risboro's lower bound for set disjointness that requires communication N uses a non-product measure. But somehow this, I don't know how to do that in this setting. It would be really interesting and it would solve this really nice open problem if you could do it. Let me stop. Okay.
Any questions?
Any other examples?
Any constraint, any problem with where sort of there's in addition to xi squared minus xi, there's another sort of identity or working modulo, seems to suffer from a similar problem because so it would be fantastic to do this for anything anything other than 0, 1 to the n. So for instance, another great problem would be to look at SDPs for planted cliques in GN1/2. So now we have, in fact it was just presented probably a week ago or 2 weeks ago here, strong lower bounds for that in sum of squares. And the reason you can't get PSD rank lower bounds for that problem, so you want to show that small semi-definite programs cannot find out that there's cannot find a clique planted in GN1/2. GN1/2 should have cliques the size of 2 log n. You plant a huge clique there, size n 10 to the 1/4 or something. You want to show that the SDP can't find it. Yeah, so applying this transference idea runs into the same problem. That now the cliques, the structure of cliques is, actually, things look a little better because somehow a random graph is kind of, it's not symmetric at all, but it's sort of like measured theoretically symmetric because like if I just restrict my attention here, I just see a random graph with a smaller p value. But okay, I don't know how to do it. The same thing arises. That now, sort of the set of cliques in a random graph, if we think about it as a subset of 0, 1 to the n, then of course it's a very restricted subset, only the ones corresponding to cliques. So again, it runs into the same issue.
Any other questions? Let's thank James for all his wonderful series of lectures.